let's cover paper 3 from the May 2019 exam version 2. This one has 3 questions in section A, and of course we are only doing the astrophysics section, or option, in section B. So we've got this circuit here where we have a battery that is a battery that does have an internal resistance. We're not taking it to be an ideal battery. We've got some resistor out here, some variable resistor, it looks like. I've got an ammeter and a voltmeter, and then we measure the current and the current coming out of the battery and the terminal voltage of the battery. That data, and we get this set of data in a graph. Student has The student has plotted error bars for the potential difference. Outline why no error bars are shown for current. So we got error bars for voltage, but what about current? Well, if we look over here, we're looking at currents in the range of hundreds of milliamps, and the error is plus or minus 1 milliamp. It's plus or minus 1% of these values. Those error bars are so small we can't see them, or they're negligible, so they need not be included. Negligible compared to the size of these, so they need not be included. So that's that one. Not too bad. Now, part B, determine using the graph the EMF of the cell, including the uncertainty for this value. Give your answer to the correct number of significant figures. Well, if we look at this, and let's fix these voltages here. Well, the potential, let me restart that sentence. The terminal voltage is going to be the EMF minus the voltage lost, or the voltage drop, through that internal resistor, which is I times the internal resistance. Now, if we rearrange this a little bit, we get that the voltage is equal to negative internal resistance times current plus the EMF. Why did I rearrange it like that? Well, if we look at our graph, we've got current on the x-axis and terminal voltage on the y-axis. So that V is like a y, that I is like an x, that negative R must be the slope, and the y-intercept must be the EMF. So if we did not get this straight line, we just got the data points on those error bars. If I can make a best fit line and find the y-intercept, there you go. I have the EMF. It's going to be the terminal voltage when there's no current running through the battery, which makes sense because if there's no current running through this resistor, it doesn't have a voltage drop. So the potential difference would just be the EMF. Makes sense. So draw a nice line of best fit, or best fit line, with a ruler. I encourage a transparent ruler so you can best see where all the points are underneath your ruler, as well as not underneath your ruler. And I got a best fit, or a y-intercept of 0, or 1.60. If we look right here, it goes right through 1.60. So my y-intercept was 1.60, and from the graph with estimated best fit line, okay. And then we need the error in that. What's the error in that? Well, the error in our voltage in each reading is plus or minus 0.02 volts. So that's what I made the error in my y-intercept, is 0.02, because it was on the voltage axis. They also accepted anywhere from 1.59 to 1.61, so not a very big variation, although this data is pretty tight. So you're not going to be able to get that much variation. 1.59 would be there, 1.61 would be there. That is pretty precise, though. And then for this, they allowed plus or minus 0.02 or 0.03 volts as an error. Outline without calculation how the internal resistance can be determined from this graph. Well, the internal resistance is the magnitude of the slope of the line. So just make the best fit line and calculate the slope. Easy peasy. Now, in the scoring guide, they say it is determine the gradient slope of the line of best fit, and then R is the negative of this gradient, because, well, the the gradient or the slope will be negative, and the internal resistance is not negative, it's positive, so take the negative of the negative, you get a positive. But I said the magnitude. Either way, that sort of thing should be fine. Okay, next part. So now an experiment is conducted to determine how the fundamental frequency F of a vibrating wire varies with the tension in the wire. The data are shown for the in the graph. The uncertainty in the tension is not shown. Draw the line of best fit. So here you may notice if you take a ruler, it's not, there's no way you can make a line of best fit through here, because any legitimate best fit line must go through all the error bars, right? It cannot be outside of the bounds of the error bars. So with a straight line, we cannot do that with these data. So I made a curve that goes through all the error bars. This is one point, and that one point was just for any curve that passed through all the error bars, which maybe they don't want to say any curve, because then you could have gone crazy. You could have gone like that, although that wouldn't be a function, so never mind, you couldn't do that. But it doesn't say any function, it says any curve. However, I can't imagine you get points for some wacky line that go through all these, but also does all kinds of stupid stuff. B, it is proposed that the frequency of oscillation is given by F squared is equal to K times T, where K is a constant. Determine the fundamental SI unit for K. Okay, so F squared is equal to KT. What I did is I solved for K. So you could just figure out, you could just say, well, the unit has to be the same on both sides. Figure out the unit of that, figure out the unit of that, figure out what that unit must be to make it the same on both sides. This time, though, I decided to solve for K and do it more directly. So K is going to be frequency squared divided by tension. Well, frequency is measured in hertz, so this will be hertz squared. Tension is measured in newtons. Breaking newtons down into fundamental units, it's kilogram meters per second squared. Notice, by the way, I did not say equals. Because it's not equal to that. These, I'm saying this implies this, because these are just the units. So Newton is a kilogram meter per second squared. That comes from F equals ma. Net force equals mass times acceleration. Kilograms times meters per second squared. And then hertz, hertz. Hertz are just 1 over seconds, or inverse seconds. The square applies to the 1 as well, but 1 squared is just 1, so I only put the square in seconds. And then we can fix our double fractions here, bring that seconds up there, bring that seconds down here. And then the seconds cancel out. We get 1 divided by kilogram meters. And so it's written in IB terms as kilogram to -1 times meters to -1, or you can just do 1 over kilogram meters. That's fine too. Write down a pair of quantities that, when plotted, enable the relationship F squared equal to KT to be verified. There's not just one correct answer to this, but the easiest one is just F squared versus T. And then that's like Y equals MX. And then if you do get a straight line where the slope is K, you're good. And it goes to the origin, you're good. Describe the key features of the graph in B2 if it is to support this relationship. Well, it should be directly proportional, meaning it's linear and it goes through the origin, with slope equal to the value of K. What were they looking for? They wanted it to be a straight line or constant gradient or linear, and it passes through the origin. Directly proportional implies both those things. However, it might be a good practice to say linear and linear passing through the origin, just to be super duper safe. However, any grader would know that directly proportional necessarily implies you're going through the origin. At least they better. Okay, now we've got a third situation in section A. So as soon as it uses Young's double slit apparatus to determine the wavelength of light emitted by a monochromatic source, we have the fringe separation S, measured with an uncertainty of 1/10 of a millimeter. Slit separation D is negligible uncertainty, and the wavelength is calculated using that relationship. That equation is, of course, given to you in your data booklet. And then they say when D equals that, S equals that, and big D equals that, determine the percentage uncertainty in the wavelength. Okay, so this is all multiplication and division. So we just add the fractional uncertainty in S to the fractional uncertainty D to the fractional uncertainty in big D. So the fractional uncertainty in lambda, which is delta lambda over lambda, is equal to the fractional uncertainties in S, delta S over S, plus the fractional uncertainty in little d delta little d over little d plus the fractional uncertainty in big D delta big D over big D. Well, the uncertainty in the slit separation was negligible, so this is 0. And so we just have to account for these two. We know the absolute uncertainty in the fringe separation is 1/10 of a millimeter, so I put 1/10 of a millimeter. And then the separation between them, between the fringes, was 9/10 of a millimeter, so divide by 0.9. And then for big D, we had 280 for the absolute size. And then the uncertainty was, where did it tell us the uncertainty for that? As divisions of 1 millimeter. So that means that the uncertainty is 1/2 millimeter. You typically, when you're doing analog measurements, the uncertainty is 1/2 of the smallest increment in your measurement device. The smallest increment is 1 millimeter, so the absolute uncertainty is 1/2 of a millimeter. When you do that in your calculator, you get 0.11, which is 11%. Explain how the student could use this apparatus to obtain a more reliable value for lambda. So reducing that error of 11%. Well, the way I said it was to decrease D, the fringe or the slit separation. So make the slits closer together. That would increase S per this equation, right? If D gets smaller, little d gets smaller, but big D stays the same, the wavelength of the light coming in stays the same, that must mean S gets bigger because this side has to be the same. Or has to not change when you change little d. So S would get bigger. Well, what that would do is increase this number while leaving that number the same size, therefore decreasing this fractional uncertainty, therefore decreasing the overall fractional uncertainty. And you wouldn't have to worry about what you're doing to the uncertainty here because they tell us the uncertainty is negligible. Now, another way you could do it, and actually probably a better way to do it, would just be to increase the distance big D, because then not only are you reducing your fractional uncertainty here because you're making this number bigger and that number stay the same, but you also are going to make the separation larger. The fringe separation is also going to get larger in this case. So then that would stay the same, but that would get bigger as well. So you'd be making the error smaller on both of these fronts. So that would probably actually be the better way to do it, but this works. Okay, now on to the astrophysics stuff. Outline the process that produces a change in luminosity with time in Cepheid variables, which is a type of star. Okay, well, Cepheid variable stars expand and contract. As they expand and contract, their temperature increases and decreases, or decreases and increases, therefore changing their luminosity, because luminosity is proportional to the fourth power of temperature. Let me look real quick to compare what I wrote to the scoring guide. They said they gave 3 different possibilities for points, and you get 2 maximum points. So they said they expand and contract, or the radius increases and decreases, or the surface area increases and decreases for the first point. The second point, they said surface temperature decreases and increases. Okay, I got those 2. And then for the third possible point, surface becomes transparent, then opaque. I did not say that one, but it's 2 points maximum. You only need 2 of them. They said specifically not to reward a change in luminosity or brightness, given that that's the framing of the question. They tell you that the luminosity or brightness changes. Okay, next part, explain how Cepheid variables are used to determine distances. Well, there's a correlation between the frequency of the luminosity change and the maximum luminosity of the star. So if you can measure that frequency, then you know L, and then you can measure apparent brightness and get the distance via this equation right here. Now, in the scoring guide, they said period instead of frequency. That's fine. You can do it either way. And so this was worth 2 points. So one of them is for peak luminosity, depends on the period, or more luminous Cepheid variables have a greater period. I got that here. And then measurements of apparent brightness allow distance determination or a mention of that equation. I got that point in two ways. So yeah, that's pretty much what they're looking for there. All right, so we have the following data for a Cepheid variable delta Cephi. Peak luminosity, distance from Earth, pretty far away, and peak wavelength of light. I guess it's actually not that far away in universal or even galactic terms. That would still be within our galaxy, for example. Determine the peak apparent brightness of delta Cephi as observed from Earth. Well, okay, well, apparent brightness is this equation right here. It's in your data booklet, right there. And they tell us luminosity. Great. We know pi, the distance from Earth. They give us the distance from Earth in parsecs. So we have to convert that to meters because this requires meters for the distance. So it's 273 parsecs times 3.26 light years per parsec, and then times 9.46 times 10 to the 15 meters per light year. Then, of course, you square all of that. And you get 8.64 times 10 to the negative 10 watts per square meter. Calculate the peak surface temperature of delta Cephi. Okay, well, we can look at the peak wavelength of the light. Right, that's on that graph that looks like this. So the intensity versus the wavelength, and it goes, oh, it's a little bit more asymmetrical than that. It should be more like that. And this peak wavelength there, where you have the peak intensity, that's what that is. And so we can use that to determine the temperature. So this is also in the data booklet, this equation. Lambda max is times t is equal to 2.9 times 10 negative 3. Solve it for t, plug in the lambda max, and they even give it to us in meters. We don't have to, they're not being tricky and giving it to us in some weird unit and hoping we either don't notice that it's in the wrong unit or making us convert. You just do the division, you get 6,800 Kelvin. Astronomers claim to know the properties of distant stars. Outline how astronomers can be certain that their measurement methods yield correct information. I said if predictions made on the basis of their models and calculations are verified when applied in subsequent experiments and observations by others, then they know that they're probably correct. What did they say in the data or in the scoring guide? Data subject to peer review or checks by others. Compare light from stars with Earth-based light sources. Yeah, that's interesting. Measurements are corroborated by different instruments or methods from different teams. Yeah, so there are a few ways you could answer that sort of question. All right, number 14. The Hubble constant is 2.3 times 10 to the negative 18 inverse seconds. A galaxy is 1.6 times 10 to the 8 light years from Earth. Show that its recessional speed as measured from Earth is about 3.5 times 10 to the 6 meters per second squared, or 3.5 million meters per second squared, or 3,500 kilometers per second. Well, they give us a nice equation in the data booklet that velocity is equal to the Hubble constant times d. We know the distance from Earth in light years, and we know the Hubble constant. So there's our Hubble constant, and then our distance from Earth. They gave it to us in light years. We have to convert that to meters. So we just multiply by 9.46 times 10 to the 15 to convert light years to meters. And then we get 3.5 times 10 to the 6 meters per second, which is exactly what they wanted. A line in the hydrogen spectrum, when measured on Earth, has a wavelength of 486 nanometers. Calculate in nanometers the wavelength of the same hydrogen line when observed in the galaxy's emission spectrum. Okay, so this is about redshift. It should be larger than 486 because the space between us and this distant galaxy has expanded during the time that light was traveling to us. So we would say, this equation's in your data booklet, that the delta lambda over lambda, which is the fractional change in the wavelength, is equal to the recessional velocity of that galaxy divided by the speed of light. So what we want is the change in the wavelength, so we can then add that to this and get our new wavelength that we are going to observe on Earth. So I just multiply the lambda up there. And so then I put the lambda in, 486 nanometers, well, that's 486 times 10 to the negative 9. Nano means billionth. Now, this is improper scientific notation. Proper scientific notation, you're supposed to have your number between 1 and 0. So this would really be 4.86 times 10 to the negative 7, but I prefer to do things in thousands, millions, billions. Times the velocity that we got up there, 3.5 times 10 to the 6, divided by the speed of light, 3.00 times 10 to the 8. It seems silly to put 3.00, but that's what they give us in the data booklet, is that the speed of light is 3.00. So that's what I tend to put here. You can put 3 times 10 to the 8, but this way I can still preserve a claim of 3 sig figs. And then you get 5.7. Well, I guess I can't because this was 2 sig figs. You get 5.7 times 10 to the negative 9, which is pretty close to 6. So that's how many nanometers our wavelength is going to change. And so I just rounded to nearest nanometer. And so our change is going to be 6 nanometers. So then we just add them together. 486 plus the 6 is going to be 492 nanometers is what we are going to observe on Earth. Outline how observations of spectra from distant galaxies provide evidence that the universe is expanding. Well, the observed redshift is indicative of the expansion of space, and we see this for all galaxies in accordance with Hubble's law. Well, nearly all galaxies. I should put a little asterisk on that because, of course, Andromeda is the one galaxy we don't see that for. So maybe I should say nearly all galaxies, because there's one exception. What they say is simply all galaxies exhibit redshift. All distant galaxies exhibit redshift. Well, I guess maybe they get around that because they said all distant galaxies, and Andromeda, as far as galaxies go, is not very distant. Number 15, we have an HR diagram that shows several types of stars. The luminosity of the sun is L sun, which is there at 1. Identify on the HR diagram the position of the sun. Label the position S. So, well, the sun's going to be there, and then the sun's temperature is about 6,000 Kelvin. So I made it even with 6,000. Now it's actually a little bit less than that. I think it's actually more like 5,800 Kelvin, but 6,000 Kelvin is close enough for our purposes here. So right there. And then the scoring guide, they allowed you to put it really anywhere in this range. As long as you were on the main sequence and at the right luminosity, you were fine. Suggest the conditions that will cause the sun to become a red giant. Well, as the sun consumes more of its hydrogen fuel, it will reach a point when it begins fusing helium in the core. Right? You'll have a core of helium that will start to fuse it, but you still have a shell of hydrogen that's fusing. I didn't say that in this answer, but that is true. This will increase outward radiation pressure and cause the sun's radius to expand to reach a new hydrostatic equilibrium between outward radiation pressure and inward gravitational pressure. And when it expands, it's going to become a red giant. Scoring guide, let's see what they said. The fusion of hydrogen in the core eventually stops, or the core contracts. I didn't specifically say that, so I don't know that I would get that possible point. The hydrogen in a layer around the core will begin to fuse. I didn't specifically say that either. The sun expands and the surface cools. I said it expands, I didn't say the surface cools. Helium fusion begins in the core, I did say that, and the sun becomes more luminous or brighter. You know what? I might have only gotten one of the 3 points on this. This is one of the things I don't like about these sorts of questions, because are those any of those things I didn't know? No. But are there things that I thought to include here, or that I thought needed to be included here? Well, in this case, no. I can see why someone would include that. But yeah. So just try to do your best on these. Usually it goes well. Usually I get all the points, but this one I might have missed as many as 2 of the points. My goodness. Okay, part C, outline why the sun will maintain a constant radius after it becomes a white dwarf. Well, nuclear processes have ceased with a constant inward gravitational pressure balanced by a constant electron degeneracy outward pressure. So I think just electron degeneracy, yeah. Electron degeneracy Electron degeneracy prevents further compression. They say, ignore any mention of the Chandrasekhar limit. Okay. Word 0 for any answer. Mentioning radiation pressure or fusion reactions. Notice as the nuclear process have ceased. Yep. Okay, good. I did not mention radiation pressure. Why? Well, because in a white dwarf star, there's no fusion. There's no more nuclear processes because the nuclear processes have ceased. Okay, part D. During its evolution, the sun is likely to be a red giant of surface temperature 3,000 Kelvin and luminosity 10 to the fourth or 10,000 times the current luminosity of the sun. Why will it be more luminous even though it's cooler? Because it's got such a much larger surface area. Later, it is likely to be a white dwarf of surface temperature 10,000 Kelvin and luminosity 1/10,000th that of the sun. Why such a smaller luminosity if it's hotter than the sun? Because it's going to have a much smaller surface area. Calculate the radius of the sun as a white dwarf, or the ratio of the radius of the sun as a white dwarf to the radius of the sun as a red giant. So they gave us luminosities and temperatures. These are both in this equation with other things. And the other things are going to include the radius, which is important, right? The radius is going to be included in the A, which is what we want. So the way I did it is I did a ratio of the luminosities. Another way you could do it is to solve this for R, right? Because A is going to be 4 pi R squared. That's the surface area of the sphere. Solve this for R and then do it. That actually I think would be the preferred method, but that's not what I did. So then the luminosity of the white dwarf over the luminosity of the red giant will be Stefan Boltzmann constant times 4 pi R white dwarf squared, T white dwarf to the fourth, and then 4 pi, Stefan Boltzmann constant 4 pi radius of the red giant squared, temperature of the red giant to the fourth. Those constants all cancel out. If you solve for the radius of the radius of the white dwarf to the red giant, you just bring this over there and bring this over there. So this is going to end up in the numerator. This is going to end up in the denominator. You see, we swap them. And we're going to take the square root because we need to get rid of the square there. So we're going to end up with the square root of the luminosities. And the square of the temperatures, because we had a fourth power, take a square root of fourth power, get a square. And so just plugging it and chugging our numbers, 1/10,000th divided by 10,000 for the luminosities, and under a square root, and then times 3,000 divided by 10,000 squared for the temperatures, and we get 9 times 10 to the negative 6. That means that the white dwarf is going to be only 9 millionths the radius of the red giant. Pretty big difference. And that is this entire paper 3 for 2019 May version 2. Have a nice day.